This is the last example from pre-calculus section 2.6 that we just didn't have time to get to in class, but it is such a valuable example that I wanted to make sure that you can follow along with this one in your notes as I go over it and fill these things in. So just like with the others, the first thing we would do is we would factor this as much as possible to see what we can get. So we notice there's an x that can be taken out of our numerator. And then we notice, wait a minute, that's the difference of two squares. So unlike a couple of other ones that I just finished with the homework, this one ends up being really nice and factorable. And then for our denominator, a 2 would come out of that. And then we just look for two numbers that would multiply to -4 and add the 3, and again, very nicely, that factors. Now what that does for us is it opens up a fact that we had in one of the problems that we already talked about, and that is this is going to have a hole. We see the x plus 4s would actually cancel, and that means this graph is going to have a hole at x equals -4. So my next question would be -4 what? You know, I would want to know where that's supposed to be. And to find that out, I can't go back to the original because if I do that, I'm going to be dividing by 0. So what I have to do is take my -4 and plug it in for x to see what we would get here. So we would get -4, and then we'd have -4 minus 4, which is going to be -8 for a total of 32 in the numerator. And then -4 minus 1 is -5, and -5 times 2 is -10. So we could really just put this in as -3.2 since we're going to be graphing that anyway. So really wanted to get that point and kind of get it out of the way so that we know where that's going to be located at. And mark that big time so that we remember this graph has a hole in it. Now with all of that nice factoring, we have all kinds of information that we can get. And again, I'd much rather go after the vertical asymptotes and horizontal asymptotes before I start talking about intercepts. So my vertical asymptotes are going to be the things in the denominator that would give me a 0 that did not cancel out. And that's what we see right here. So that would be x equals 1 because 1 minus 1 would give us a 0 there. That's the only vertical asymptote we get in this graph. Then we talk about horizontal asymptotes, and we see this would be infinity cubed, and this would be infinity squared. So if we were to cancel out a couple of those, we'd have infinity to the first up at the top. Well, that's going to keep going forever, and so we're not going to get a horizontal asymptote with this one. That's just going to be none. So now let's go back and talk about those intercepts. The x-intercepts are wherever we can make that numerator equal to 0, because the x-intercepts are always something 0. So we want to know what that something is. Well, to find that, we could go back to our factored form and we could say, well, here it would be 0, here it would be -4, but we know we have a hole there, so that's not going to be an x-intercept, and this would be +4. So we would have x-intercepts at 0, 0, and 4. 0. Again, because that is all about that numerator equaling 0. Then our y-intercept, well, that's what we're going to get if we put a 0 into this formula, because that's our x. To get the x-intercept, you need y to equal 0. To get the y-intercept, you need x to equal 0. And it's up to you if you want to go back to the very first one, or maybe you like this factored form. It makes absolutely no difference as long as your factoring is right. So let's say we're not sure about our factoring. 0 minus 0 will give you 0 over 0, 0, -8. 0 divided by -8 is 0, 0. So that is both our x and our y-intercept at 0, 0. So we have quite a bit of information at this point, but what we would want to do is think about how we could use those limits to kind of guide that. So let's go ahead and put any of the information that we have so far on here. We had a vertical asymptote at x equals 1. We did not get a horizontal asymptote. We do have 0, 0, and 4, 0 as points on this graph. So now what I think is, well, there's got to be something more than this. I mean, this is a hyperbola. And that's because in this problem, the degree of the numerator is greater than the degree of the denominator. If you go back up here to the beginning, you'll see that's what's going on. That means this will have a slant asymptote. So to find that slant asymptote, we are going to need to do long division. I would prefer not to do it with this one, and that's because it's just going to take longer than our nice factored form. So our nice factored form, if we go ahead and distribute, would be x squared minus 4x divided by 2x minus 2. And that's what I want to do to figure out that slant asymptote. So let me see if I can find some space here to do that long division. So we will take x squared minus 4x, and we will divide that by 2x minus 2. So we need to take our 2x minus 2 and figure out, well, what do you multiply that by in order to get 1x squared? Well, I need another x for the x squared, and I think, well, what do you multiply 2 by to get 1? Well, you multiply it by 1/2. So yes, sometimes we have to use fractions as we are doing our polynomial long division. So if we multiply 1/2 x times our 2x minus 2, and that almost looks like I've got a little x squared going there, so hang on a second. 1/2 x times 2x minus 2. There we go. That's going to give us 1x squared, and then 1/2 x times negative 2 will give us minus an x. Now, it did what we wanted it to do. It matched up with that x squared, so we're going to need a 1/2 x right here. And then we would go ahead and change the signs and add. So x squared minus x squared is gone, and negative 4x plus x is negative 3x. And I don't have anything else to bring down, so I'm just going to put a 0 there. So now I have 2x minus 2, and I need it to be a negative 3x. So I need to think, I want something times 2 to give me negative 3. Well, you just do a quick little algebra, that's going to give you negative 3/2, or you just think through it in your head, however you want to do it. We're going to need to multiply this by negative 3/2. So that'll go up here, and negative 3/2 times 2x will give us our negative 3x. And then negative 3/2 times negative 2, that's going to give us a positive 3, so plus 3. So then we need to change the signs and add, and that will give us a negative 3 for a remainder. But notice how I changed colors here, and that's because we don't need that remainder. This was what we needed for that slant asymptote. So slant asymptote, so it's readable, slant asymptote is going to be at y equals 1/2 x minus 3/2. And I'm going to erase this because I need the space. Got a lot to take care of here. So I'm going to go back and put that slant asymptote on there using y equals mx plus b. So we're going to need to start on the y-axis at negative 1.5. And then from there we need to go up 1 and over 2. And we could go back 2 and down 1. So that we can get the asymptotes that we need here. That one's a little low. All right, so as I look at this, because we have that slant asymptote, I envision that this is going to be one that has 2 branches that are going to be symmetric to each other. And if that's the case, what we should see is one doing this and another one doing this. Now that's enough, that thought of what I see there matching up with the numbers, to help me discuss those limits for my vertical asymptote at 1. So the limit as x approaches 1 from the negative side, the left side of f of x, is, well, as we approach, we are going up. And I want to wait to make that solid until we're certain about everything. So that's going to be infinity. And the limit of f of x as x approaches 1 from the right-hand side, so f of x as x approaches 1 from the right, got a little carried away with my plus 1 on the right-hand side. Well, as we approach our 1 from the right-hand side, this is going down. So negative infinity. All right, where do we go from there? Well, let's just talk through the rest of this and figure out where we can get the rest of our points, the rest of our knowledge. And because we already saw that slant asymptote, we have a pretty good idea of what's going to take place on each side of this. But we really should put some numbers in. So we should maybe put in a 2, a 3, and again, you wouldn't have to go all the way back up to the original. You could use the one that we used when we were planning that slant asymptote, when we were doing our long division. So we could use x squared minus 4x over 2x minus 2, or you could use the factored form of that. Whatever is easiest for you to do the math, that's what you want to do. But you need to take that 2 and plug that in there, and I'm going to tell you that that comes out to negative 2. And this part we would do by hand, because remember, we're not supposed to be using our graphing calculator. And we could put a 3 in there, and that'll come out to negative 3/4. So let's take a look at 2. We are at negative 2. And at 3, we are at negative 3/4. And that is right in line with what we knew was supposed to happen. Now on the other branch, I want to be careful, and that's because I already know that there's going to be a hole. We don't want to forget that information. Let's go back up here and remember where that hole is going to be located. That's going to be at negative 4, negative 3.2. So let's put that on there. Right about there is where our hole is going to show up. So we'd want a couple other numbers on there. Let's see, maybe I'd just pick negative 2. And again, you can put that back into either one of these two, but you're going to get negative 2. So negative 2, negative 2. And then I know that it's going to approach that asymptote, so really I wouldn't even need another point. But if it's a test and you just want to double check, maybe put negative 5 back into any of those equations that we have, or any of those functions that we have, and we'll get negative 3 3/4. So 1, 2, 3, 4, 5, 1, 2, 3, and 3/4. But that just verifies what we already knew about this. You know, it has to approach those asymptotes and get super close to them without crossing over. So now we think domain, and domain is about the x's, and from this arrow we can absolutely see that we are going to go right forever, so negative infinity. But we do know we have a cutoff, and that cutoff is, well, first of all, the negative 4, because what we do is we think, as we travel along this graph, what do we have to leave out? And that is a hole right there at negative 4. So we're going to stop at negative 4, we're going to hop over it, and then we're going to get back on our graph, and we're going to travel until we get cut off by our x's, and that's going to be at 1. So this is going to go from negative 4 to 1. Got to jump over the 1, but then we are going to the right forever. So infinity. So our domain, you know, not the worst one that we've talked about in class, but that is a pretty complicated domain. Our range, well, we can see we're definitely going down forever. It doesn't matter which of these we look at, and we are definitely going up forever. So like the range, that one's negative infinity to infinity. We don't have anything to worry about there as far as finding any jumps or breaks. Continuity, well, remember, all of these are continuous along all the x except where we have a hole or a vertical asymptote. So we know negative 4 and 1 have to be left out in this graph. Increasing and decreasing. Well, we have a continuous branch on the left side and a continuous branch on the right side. It's just a matter of figuring out what's going on. And if we are drawing this graph avoiding that 4, we are increasing, we are going up. So from negative infinity to 1, we are increasing. And then the other side of the branch is also going up as we draw it, just as we would read it from left to right. So that is also increasing, and that is from 1 to infinity. Symmetry? No, I mean, we're talking about even or odd symmetry, and this is not going to have that. So that's a no. Bounded? Remember, we had a range here that was negative infinity to infinity. So that's a no. That is not bounded. And then local extrema. Well, no, we don't have any local maxes or local mins. This is nice and continuous and flowing, so we don't have any of that. But we have some end behavior. I mean, that's just going to happen. So limit as x approaches negative infinity of f of x, and limit as x approaches positive infinity of f of x. So let's go back and see what's happening as we go to the left forever with this graph. And as we travel to the left forever, we are going down. As we travel to the right forever, we are going up. So negative infinity gets negative infinity, and positive infinity gets positive infinity. And that's example 9, which is, it's a really good one for you to look over.